for discussion or today's topic for learning is construct binary tree from a pre-order and in-order vector array. So we are given actually a vector array of pre-order and a vector array of in-order. We have to construct a binary tree from out of it, and we can see that the property of the pre-order and the in-order are as follows. Pre-order is we print the root first, then we move to the left, then we move to the right. Similarly, in order, we have to move to the left, then we print the root, then move to the right. So we will just do a quick pre-order check for this given example: 3, 9, 20, 15, 7. So 3 is the current root. Alright, so we have to include it. 3 is included. Then we move to as the property states, root left, right. Then we move to the left. 9 has to be included. Alright, then as this is the current root, 9 was included, and as we can see, the current root 9 has no left or right children. So we have to move back. We move back. We have seen that 3 has covered all its left children. Now we have to move to the right. When we move to the right, 20 is the current root. We have to include 20, which is included. Then we have to move to the left as the pre-order property states. We move to the left and we find 15. 15 has no further left or right children. So we have to first include 15, and then we check left, and then we check right. There are no such children nodes, so we move back. Now we can see the current node 20 has covered all its left children. Now we have to move to the right. 7, we have included 7, and that's how the pre-order vector is made. Now similarly, the in-order vector is also made, which is 9, 3, 15, 20 and 7, and as the property states, left, root and right. First we have to move to the left. We have to 3 is the current root, then we move to the left, 9, which is the current root, but now we can see that there is no further left nodes, so we have to include the root node, which is 9. We have included 9. Then we move, as we have included 9, we have to move to the right, but there is no further right, so we move back. And now we can see that we have covered the current node is 3, and we have seen that we have covered the left portion, so we have to include 3, as this is the current root node and has its left covered as the property states. So we include 3, then we move to the right. We move to the right, and then we find that it has a left node. We move to the left. We have to include 15, as there is no further left, so we have to include 15. No further left, then we check root. Root 15 is included. 15 is included. We move to the right, and there is no further right, so we move back. The current root is now 20. 20 is 20 has its left part covered, so we are going to include 20. 20 is included. Then we move to the right as the property states, and in the right there are no further left nodes, so we have to print the right node, root node. Then we print the root node. There is no further right nodes, so we traverse back. So that's how we have made the pre-order and in-order traversals. Now that we have a good understanding of the pre-order and in-order traversals, we can see the property plays a big role in today's question, which is construct binary tree from pre-order and in-order traversals. We are given a pre-order traversal and we are array, and we are given an in-order traversal array. So we can see that if I talk about the first node, the first, which is 3 itself, right? So 3 is the root, as the pre-order property states. The first one is the root, then we move to the left, then we move to the right. So 3, when I talk about the first element in pre-order traversal, it has to be the root node, so it is the root node. Let's say, so 3 is the root node. And if we talk about in-order traversal, we find this 3 here, right? So can we think about something like 9? Where is 9 situated in the current binary tree example? It is situated to the left. And 15, 20 and 7, where are they situated in the current binary tree? They are on the right of the current node 3, right? So we can see this property as all the elements to the left in the in-order traversal are situated in the left of the binary tree, and all the elements situated in the right in the in-order traversal are on the right of the binary tree, as the property states. So we are going to use this property only to make or construct our binary tree. And if we talk about the algorithm, this is as simple as that I have discussed right now. So let's move to the algorithm. Algorithm would be that we first check 3, which is in the pre-order, which is the first element in the pre-order, which is our current root. So we make a tree of 3, the current root. So now the current root is 3. We have made a new tree node which has the value 3. So we can say that we have to check for the value 3 in the inorder vector array. When we find the value 3, we have to note the index of inorder, where we have found 3. All right. So by that, what I mean is, let's construct a tree. 3 is the current root node. So we have found 3. We have found the index of the current root node 3 in the Inorder Traversal array. All right. So we have also discussed the property that this array will the left value is only. So the left value is only 9 here, and let's talk about the right values. Right values would include 15, then we have 20, then we have 7. All right. So these are the possible values on the left, and these are the possible values on the right. So we have to only check for the if we move to the left, we have to only check for the values in the left, and if we move to the right, we have to only check for the values in the right. So let's say we first move to the left. We first move to the left of the Inorder Traversal vector array, and we can see that we have to connect it with the left of the current root node, right? And as we can see, there is only one element, so the current inorder index would return this only, so we will include 9. And then we move to the right of the current element index 3, which has 15, 20 and 7 to its right, and we will have to choose from these in this. So how will we choose it? It's simple. We have covered 3, then we have to then we will look at 9. All right, 9 was included here because we traversed left first, and the pre-order traversal property states the left first. So all right, we have covered 9. Then we move to the right, which is 20, right? So the right part has to be 20 because there is no such element on the left. So from this we get 20. That would mean that the left part of 20, which is 15, and the right part of 20, which is 7. All right. So if I were to make a node, we have to recursively call them, and for the current root node 20, we have the left value as 15, and we have the right value as 7. That's how we would construct a binary tree from the pre-order and in-order traversals. Let's look at the algorithm now. Algorithm states the same. So take element from pre-order and make a tree node as it is the current root node element, and find the same element in order and note its index. Then call recursion for elements on the left of the found in order index, and do the same for the elements on the right. All right. So let's look at how we will code this. This is the example. This is the same example I have just given you. So we what we are doing in the code, let's say we have first declared an global int pre-index just. So we have said that the pre-index is starting from 0, as we will be using to traverse the pre-order index in spite of the recursive call. So we are not including it in, here because we don't want the pre-order index to go back. We just want it to keep moving forward as we want. All right, because the current root node is 3, then we have to move to the current root node 9, then we move to the current root node, which is 20. Similarly, as for same for the other ones. So now we can see that we are directly returning the function solve, which takes the parameters as pre-order, in-order, and start index and end index. So end index is, note that the end index has included the last index of in-order vector array. All right. So the first base case is when the start index crosses the end index, we will have to return null. This case will occur when we have encountered leaf nodes, so it will return null. So let's say about forming a new root node. So we will first create a new node as the pre-order. All right, from the pre-order index, and the index would keep increasing. So let's say this is actually the first zeroth index for now. So zeroth index meaning the value is currently 3. All right, so there is the third value. Somehow I cannot select it, and so let's move forward. And we have to find the in order index for the third one. All right, so we will traverse the third, travels to find the third. This is basically a linear search. We are doing a linear search to find the third, the element with value 3 and its index. So when we encounter from start, we are note that we are moving from start to end only, because we have to only find in the given range. So we have the in order index we found at j. We will have to break because we don't have to move any further. We have found it. It's basically a linear search. Then after doing the linear search, we have found the in order index, and with the algorithm, as the algorithm states, that we have to include elements from the start till the in order index minus 1 as the end index. We have seen why we have done that. And similarly for the right part, we are going to use in order index plus 1 till end index. All right, and simply then return the root. So let's just run this code. It's running. We can submit it as well. All right, it has been submitted. So let's just see what just happened with the time complexity and space complexity. Let's discuss the time complexity and space complexity. All right, we have made a mistake here as well. So the time complexity for this would be, we are doing a recursive call, right? And we are inside the recursive call, we have a for loop. So that would mean the time complexity is order of n square. All right. And how about the space complexity? Space complexity would be at one time, the maximum space in the recursive the call stack would take would be order of h, the height of the binary tree. So that would be closely equal to order of n. So the space complexity is order of n, time complexity is order of n square. We have understood this solution now. Now, how can we improve this, optimize the time complexity here? As we can see that we are using a for loop inside a recursive call. Can we somehow not use the for loop to find the index? So what if I tell you that we can use a map to store the values along with their indices? So when we store the indices, we won't have to search for this linear time, right? That would drastically decrease the time complexity. That is what we want, right? So let me just comment out this code. All right, here is our second solution, in which we have introduced an unordered map which takes the value along with the indices in the inorder array. So we have done exactly the same what we have done before. So let's see the unordered map. The unordered map is here. We have introduced the unordered map. It stores the value and their index from inorder. All right, then we are directly returning the solve function, and the solve function is return null if the same base condition. Then we are introducing a root. We make a root, then we have to find the index from the inorder. Find index of the element of the same element we have taken as root, current root more specifically. All right, so root left takes from preorder to map preorder in order, then starts from the beginning start, and the end would be in order index minus 1, and similarly the right root of right would mean take in order index plus 1 till end. Let's run this code as well. submit it as well. So it has been submitted. Let's see how the space and time space complexity and time complexity works for this. The time complexity for this would be order of n, because we are just filling the call stack, which is and for the space complexity, which we have introduced in our map, we are using the call stack, and call stack would go to order of h maximum, and we have stored the n is the number of nodes, and n plus order of n plus h. So that would be order of 2n, let's say 2n, and then which is just order of n. So the space complexity is order of n, and time complexity is order of n. This is the best solution for this problem. I hope you guys learned something new, and cheers. That's all for today.